In this video, we are going to be looking at monotone sequences and bounded sequences. So first of all, what is a monotone sequence? Well, to answer that question, we need to know what an increasing sequence is and what a decreasing sequence is. The definition for increasing and decreasing sequences is pretty straightforward. It's right here. A sequence is increasing for all n greater than some arbitrary n sub 0 if a sub n is always less than or equal to a sub n plus 1. In other words, every term of the sequence is greater than the one before it. If every successive term in a sequence is larger than the one before it, it is increasing. Likewise, it is decreasing if a sub n is greater than or equal to a sub n plus 1. In other words, if every successive term, a sub n plus 1, is smaller than the one before it, then it is decreasing. That makes sense when we take a look at the graphs. So the first two examples we're going to look at here, we're going to be looking at from a graphical perspective. So here we have a nice simple arithmetic. You should recognize that as an arithmetic sequence. And even though I plotted the sequence as a straight line, we know that the sequence is simply a series of discrete points. I also called it a function. I think when I did this problem, I was thinking functions. I graphed a continuous line and I called it a function. However, we are dealing with sequences, so we're dealing with discrete points, and we will change the word function to sequence. So a sequence is increasing for all n greater than or equal to n sub 0. All right. So that means that every term in the sequence is greater than the one before it. So we can see that this term, in other words, the function is basically increasing. As we go from left to right on the x-axis, the function is increasing everywhere. Every output value is getting larger and larger and larger. All right, so monotone simply means that over the entire domain, the sequence is either always increasing or always decreasing. And so this is monotone because the arithmetic sequence for all values of n will always be increasing. So if it's always increasing or always decreasing over its given domain, now the domain may be restricted. In some cases, we will be restricting the domain. If the domain is restricted, then within that restricted domain, if it's always increasing or always decreasing, then it is monotone. In the second example, we have a decreasing sequence. Insert the word sequence there. And of course, again, we know we have a series of discrete points here, not a continuous line. So for every value, so if this is for like n equals 1, there's our term for n equals 2. Here's our term for n equals 3. There's our term of the sequence for n equals 4. So for every term of the sequence, the term of the sequence is getting smaller and smaller and smaller and smaller and smaller and smaller. If that happens over its entire domain, then it is monotone. It is decreasing and it is monotone. Now, looking at it from a graphical perspective, it sure looks like it is decreasing over its entire domain. But how do we know that for sure? How do we know that someplace out here it doesn't turn around and start going back up again? We don't know that just by looking at the graph. We may have that intuitive sense that that's what's going to happen. But what we really want to do is we want to have an algebraic approach where we can definitively know that this function is always increasing or always decreasing. And so that's what we're going to be doing now. We're coming up with an algebraic approach that will tell us if a function is monotone. So given this particular function, a sub n is equal to 3n over n plus 2, we have to create an a sub n plus 1 according to the definition. So all we have to do is add 1 to every n value. And so that's what I did here. Added 1 to every n value. and then simplified that a little bit. So what I've done here may look a little confusing. I just put a little empty box with a little question mark above it. And the reason I did that instead of a less than or equal to sign or a greater than or equal to sign is because I don't know which one to put in there. What we want to do now is we want to determine, is a sub n less than or equal to a sub n plus 1 for all values of n in the domain, or is a sub 1 greater than or equal to a sub n plus 1 for all values in the domain? We don't know which one of these symbols to put in here, if either one of them. And so that's why I put the little empty box. We can eventually just fill in the empty box with the appropriate inequality symbols. So let's get started. Right here, I put in my a sub n and my a sub n plus 1. And so what we want to do is we want to algebraically play with this, like we love to do with algebra. And so I multiplied both sides by the least common denominator, which is n plus 2, n plus 3. In other words, I cross-multiplied. And so that gives me this and this. Multiplying those terms together, I get 3n squared plus 9n. Over here, I get 3n squared plus 9n plus 6. Well, those are very similar to each other. In fact, they both have a 3n squared, so if we were to subtract that from both sides, they would cancel out. If we subtracted 9n from both sides, they would cancel out. And so what I'm left with is 0 and 6. All right. Well, now I can fill in that 0 is always, always, always less than or equal to 6. And because 0 is always going to be less than or equal to 6, we can say that this is true for all values of n. And so in other words, a sub n, which is on the left-hand side, will always be less than or equal to a sub n plus 1 on the right-hand side. So that means that it is an increasing function because every successive term, a sub n plus 1, is greater than the previous term for all values of n in the domain. So in other words, this is true for all n. The sequence is increasing for all n in the domain. Therefore, it is increasing and monotonic, or monotone. Some textbooks will say monotonic. Some textbooks will say monotone. Let's try that again. So here we have another sequence. We're given a sub n. So let's create an a sub n plus 1 by simply adding 1 to the n value. And what we want to do is we want to see, is a sub 1 less than or equal to or greater than or equal to a sub n plus 1? Which one of those inequalities do we want to use? And so to do that, again, we have to use a little fancy algebra. I put my a sub n on the left-hand side, my a sub n plus 1 on the right-hand side, and then what do? Well, we know that we can take 3/4 to the n plus 1 and divide it by 3/4 to the n if we wanted to. So in other words, I showed what I'm doing over here. I divided both sides by 3/4 to the n. That gives me a 1 on the left-hand side. And that gives me this on the right-hand side, which 3/4 to the n plus 1 divided by 3/4 to the n. And then I simplified it to 3/4, and I showed the actual simplifying here. 3/4 to the n plus 1 can be broken up into 3/4 to the n times 3/4 to the 1, divided by 3/4 to the n. Those then cancel out, leaving us with just the 3/4. Make sure the algebra makes sense to you. The important thing is this will reduce to 1 on the left-hand side, 3/4 on the right-hand side. Well, 1 is always, always, always greater than or equal to 3/4. So this is a true statement. 1 is greater than or equal to 3/4. It will always be true. So therefore, we can conclude that the left-hand side, a sub n, is greater than the right-hand side, a sub n plus 1, for all values of n. And because each successive term is less than the one before it, boom, 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 going down, we can say it's decreasing monotone. It is a decreasing monotone sequence. The next one, we have, let's see what pretty color, let's use violet. So we have a sub n, have to create an a sub n plus 1, simply adding 1 to all of the n values, and then simplifying it a little bit, just to make it easier to work with. So once again, I start off by saying, all right, a sub n on the left-hand side, a sub n plus 1 on the right-hand side, with my little box in the middle. You guys don't have to actually put a little box. You just leave it blank. And so I substitute a sub n plus 1. Cross-multiplying, I get this statement. Again, the 5 n's cancel out, and I have 7 on the left and a 2 on the right. Well, 7 is always greater than or equal to 2. So therefore, a sub n is greater than or equal to a sub n plus 1, which means it is decreasing and monotone once again. And the last one that I'm going to do here, we have a trigonometric function. All right. Now this one is a little bit, trickier, but right off the bat, we know that the numerator is a sine function, and sine functions are oscillating. All right. So if it's oscillating, we probably already know that it's not going to be monotone. Right. And that's pretty much all you really need to realize. I was going to go through the steps here and to show you that it can get very difficult to do this algebraically. So I created an a sub n plus 1, simplified it as much as I could, set this problem up the same way I've set up every problem, and then even if you cross multiply, you get a big mess. So you get a big mess, and so you just have a big pile of nothingness to deal with. So you have to resort to some other type of thought process. It's like, all right, well, intuitively speaking, I know that the sine function oscillates. So if it oscillates, it simply cannot be monotone. And then I also put something down here that because the sine of 3n plus 3 is a phase shift of the function sine of 3n. In other words, here's the sine of 3n. Here's the sine of 3n plus 3. And by a phase shift, what I mean is if this is the cosine of 3n, then a phase shift simply means that we're kind of shifted off to the side. You take every point and move it. Let me do that in a different color. Take every point and move it to the left. All right, move it to the left. That's a phase shift you will remember from pre-calculus or trigonometry. Well, because this is true, the functions are alternating which one is on top and which one is on the bottom. So we can't say that the left-hand function is always going to be less than or always going to be greater than. So once again, the algebraic approach really is going to get us nowhere with this. So we have to think about it intuitively. All right, now on to bounded sequences. A bounded sequence simply means that there is an upper bound and a lower bound. If a sequence is bounded above, if there exists some number m such that the term of the sequence is always less than m. So as an example, if we have a horizontal asymptote up here, and so my sequence is coming up but will never go beyond that, that would be my m, my upper bound. Okay, I'm going to draw it continuously. It makes it more. There we go. That's m is acting as an upper bound. Likewise, we could have a lower bound, right? If m is down here and the function is getting closer and closer and closer, but will never, ever, ever go beyond that. It could be equal to it, but we'll never go beyond that. Then it is a lower bound. So we are bounded below if m is less than or equal to, so in this case, m is less than or equal to the terms of the sequence. And so this is bounded above up here. It is bounded below down here. And so if it's bounded above and bounded below, we say it is bounded. It has to be bounded above and bounded below. Now, some sequences are bounded above, some sequences are bounded below, but not both. A good example of something that is bounded above and below, of course, would be like the sine function or the cosine function. They're all bounded above by 1, bounded below by -1. Okay, the function never goes above 1, never goes below -1. So we would say that the sine function is bounded above by 1 and bounded below by -1. It's sometimes difficult without actually graphing the function to determine exactly how something is bounded above or below. So let's just take, the convergence sequences are bounded. If a sequence converges, then it is bounded. Okay, so if a sequence converges, it is bounded. Does that mean if it's bounded, it converges? Maybe. But if it converges, then it is definitely bounded. And then the monotone convergence theorem simply says, if a sequence is bounded and it is monotone, then it converges. So that's combining what we just did with the monotone sequences with the bounded sequence. It has to be bounded and it has to be monotone, and then we can say it's definitely going to converge. So, first example. So we have a sub n plus 1, and the first thing we're going to do is let's determine if it's bounded. Well, one way to do this is say, okay, with the smallest value of n is going to be 1. So if I find a sub 1, by substituting 1 in for n, I get a sub 1 is equal to 1. If I continue to put values of n in there, I know that the denominators are going to get bigger, which means the whole fraction is going to get smaller. And so 1 is acting as an upper bound. It is bounded above by 1. In other words, the value of 1 over n squared will never be greater than 1. It can be equal to 1, but it will never be greater than 1. As n gets larger and larger, if we take the limit of this, we see that we're approaching 0. As the denominator gets infinitely large, the whole fraction, as we've discussed before, is getting closer and closer and closer to 0. So it's bounded below by 0. So this is a relatively easy one to determine if it's bounded. Bounded above by 1, bounded below by 0. So it is bounded. Yes. What about, is it monotone or not? So we have to go through the process we went through in the last few problems. I found the a sub n plus 1, and I'm setting it up to determine if 1 is always less than or equal to or greater than or equal to. Going through the same process that I went through in the last few problems, I set a sub 1 on the left, a sub n plus 1 on the right, do some cross multiplying, and then I see that, well, these n squared terms are going to cancel out, and so I'm left with 2n plus 1 is greater than 0, which is always going to be true. And so we know that this is that a sub n is greater than or equal to a sub n plus 1. So therefore, it is decreasing for all values of n, and therefore it is monotone. Now, once again, the reason we know this is happening for all values of n is because we're doing this generically with just using n. We're not using specific numbers. If we were using specific numbers like n equals 2 and n equals 3, and determining which one was larger or smaller, then we would only know that for 2 and 3, one was greater or smaller than the other. But when we just leave it in terms of n, we're doing it for all values of n. So because the sequence is both bounded and monotone, it therefore converges by the monotone convergence theorem. The next one, the sine function. Well, we already know sine function is not monotone. It oscillates. So that we can conclude right off the bat. We do know, however, that it is bounded, as I already discussed. It's bounded above by 1, bounded below by -1. So here's an example of a sequence that is bounded, but it's not monotone, and therefore it oscillates, and we cannot say that it converges. And we know that the sequence, one of the sine or cosine function never converges towards anything. It just keeps going up and down and up and down and up and down. So it's not monotone, and so it cannot be determined to be convergent by the monotone convergence theorem. Again, saying that it cannot be determined to be convergent by the monotone convergence theorem does not necessarily say it is not convergent. Okay? We know that it's not, but all we really can conclude from the monotone convergence theorem is that by that theorem, it's not convergent. Some functions may not be monotone, or they may not be bounded. They may not fulfill one of those requirements, but somehow they might be bounded. 3 to the n over n factorial. So, how do we determine if this is bounded? So, again, I like to start by plugging in a sub 1. That's the smallest value that I'm ever going to have for my n. And so I end up with 3. Now, as I start to increase n, what I do know, and this is from a discussion we had in one of my previous videos, the factorial is going to increase faster than anything else, even an exponential. Factorials increase faster than exponentials or arithmetics, geometrics, anything. So therefore, as n gets larger and larger, I know intuitively that this thing is going to approach 0 because the denominator is going to get larger faster than the numerator, just like I discussed in the past video. If the denominator is getting larger faster than the numerator, the whole fraction is approaching 0. So therefore, and it is bounded below by 0. We can also find this by finding, essentially what I'm doing intuitively here is finding the limit. Again, how do you know that the limit of 3 to the n over n factorial is equal to 0? You have to think that out intuitively, because we do not know how to find the derivative of a factorial. Otherwise, we could try using L'Hopital's rule. So it's bounded. It's bounded by 3 and it's bounded by 0. Bounded above by 3, bounded below by 0. And so over here, I'm not going to go through the whole process. You can kind of go through the algebra here. Right? Especially when you get to this point right here, make sure that you kind of understand what was going on here. One thing I do want to explain is that n plus 1 factorial, n plus 1 factorial can be rewritten as n plus 1 times n factorial. In other words, what we're doing here is I'm saying that, let's say, 8 factorial. What I'm essentially saying here is that 8 factorial could be rewritten as 8 times 7 factorial. Think about it. It's the same thing, because 8 factorial is 8 times 7 times 6, on and on. 8 times 7 factorial is 8 times 7 times 6, So that's what we're doing when we write it like this. Taking the n plus 1 factorial and rewriting it as n plus 1 times n factorial. Okay, so that's what I did here. That's how I broke that up. And so then the n factorials cancel, the 3 to the n's cancel. All we have is n plus 1 and a 3. Well, when n is equal to 1, then we have 2. We would have 2, which is less than or equal to 3. But then when n is equal to 2, we would have 3, which is equal to 3. When n is equal to 3, we would have 4. So whenever n is greater than or equal to 2, it will be monotone. When n is equal to 1, so we have a function that's going like this. We've got the first point here, the second point is lower, then it starts going up. But after you get to n equals 2, it will continue to be increasing or decreasing. Increasing, decreasing, yeah. A sub n is going to be greater than a sub n plus 1, so it's increasing. No, decreasing for every value. So monotone. So it is bounded and it is monotone. And so therefore it is convergent. Did I actually write that anywhere? I guess I didn't. Only monotone when n is greater than or equal to 2. If we restrict the domain to values of n is greater than or equal to 2, then we're okay. All right, last problem real quick, so I don't run over my 30-minute time limit here, is this another trig function. Okay, and so this one can be a little bit tricky. You might have to think out intuitively. We know it's not monotone because of the cosine function in the numerator. What about being bounded? Well, this is a tricky one to try being bounded. It is bounded due to decreasing oscillations. Now, how do you figure out that? That's really kind of hard to figure out. This is one I would actually just resort to graphing. Now, you should always graph. You can graph these in Desmos to verify what's going on, but in most cases, you should be able to show algebraically. On an exam, you will be required to show algebraically. This particular case, kind of not getting anywhere here. We know that the limit of this is going to be equal to 0, but I don't know if that's an upper bound or a lower bound. Here we have a value that's negative, so this is great. 0 is greater. Is that a lower bound? Is this an upper bound? It gets kind of tricky to determine what's going on. So it is bounded due to decreasing oscillations. What's actually happening is you've got decreasing oscillations. They're getting smaller and smaller and smaller and smaller, right? So it's bounded above here, bounded below, whatever that is, but finding those values can be tricky. Anytime you have something with a trig function, it's kind of tricky, but if it's a sine and cosine, you know it's oscillating, and so it's not going to be monotone. So although the sequence is not monotone, it still converges, okay? It's bounded, but it's not monotone. Right? So you might be thinking, how can it be bounded and not monotone? Because of the decreasing oscillations. As I drew this little picture over here, you can see that the decreasing oscillations, the oscillations are closing in on 0. And so the oscillations become microscopically small. They're always going to be oscillating forever and ever and ever, but getting microscopically close to 0. So we can say that it is converging to 0. And so we can actually just find that by finding the limit. So it converges to 0. So in most cases, to determine convergence of a sequence, we can just use the limit, find the limit of the function. Sometimes if the limit is not easy to find, we may want to determine if it is monotone and if it is bounded. If it is monotone and bounded, it would be convergent by the monotone convergence theorem. Still, we need to know how to find if a function is increasing or decreasing and how to determine, in most cases, if it is bounded. All right, that's it for this video.